welcome. This is ECE 2200, 2210 well, it's supposed to be, so I'm seeing some head nods. So yes, you're in the right place. So this is electrical engineering for non-majors. And then I think it's an elective for those that are in 2200. So welcome. I'm Professor Angela Rasmussen. So I've been here 21 years, so a lot of experience teaching. I am a lecturing faculty, so I love teaching, and I love to teach all of you guys. I love your aha moments, so I am here to help try to support you guys in learning. I like to set up the course to be an option where everybody can get A's. Unfortunately, that also means that everybody can get F's, so if you don't take advantage and perform, you will still get a poor grade. So what are we going to be talking about? Oh, I have the wrong QR code on this one. Let's see. 40. Okay. All right, so I like to use, there's a copy. I like to use, it's Pull Everywhere. So if you have a phone, go ahead and you can pull this out, and you can use this. Okay, putting it over there. Now it's not behind my head. Okay, so question, what have you heard that sounds interesting that was designed or innovated by an electrical or computer engineer? So it is not quite started yet. It takes me a second to get these going, but so it asks on there if to create a login. You can skip that. You can hit cancel and it will still let you in, and then you can respond on that one. So if you don't want to create a profile, just cancel it. I will go back to it in just 1 second. Okay, wrong one. Some of these have been used. Let's see. Okay, so this is kind of how I'll be asking you questions. So ignore this one that's behind my head, or was behind my head, not that QR code. And just go ahead and put on here things that sound interesting to you that you've designed or that you've heard of being designed or innovated by an electrical or computer engineer. If you want to, you can also go to the spectrum.ieee. Try and get out of your way so you can see some of these. Spectrum.ieee.org, which also has some ideas. So go ahead and spend a couple minutes. We'll kind of look through these. Computers is a great one. Graphic cards, light bulb. Radio technologies, also fun. Electric motors. Being able to use the frequency domain to analyze signals, 3D printers. Quantum computing. Induction heating, microchips. CPU, TPUs, GPUs, which wasn't mentioned yet. Electricity itself. A little typo there. I'm sure that was supposed to be iPhone. I'll correct it for you. PC parts, computer motherboards, Arduino. All right, great. So all of you seem to have heard this is behind me. All of you have seemed to have heard about some applications. So have you ever been intimidated by the application, I guess? So some of it, let me go to this. Okay, so something that looks like this. This is an application that I like. Lectures. So this application, make this bigger. So I am assuming everyone here cannot analyze this and know what is going on with this. Okay. By the end of the semester, guess what? You will know what is going on here. You can actually say, oh, this is a such and such. There's capacitors in here, there's resistors in here, there's an op amp in here. There are these components, there's a diode in here. So there are these components in here. I can now identify them for one. Two, I can actually know what voltages and currents are going on in here and what this actually produces. So that is what you're going to learn this semester, is the techniques to be able to look at a circuit that looks like scary like that and be like, okay, it's not scary anymore. I actually can identify those components and I can actually analyze them to tell me information. I know what voltage and currents I need to actually create this type of a signal output. So that's what we're going to be doing in here this semester. So while this may not be your first choice of class because it's required, hopefully we'll have some fun. You'll be able to learn these techniques and be able to do something with it that is interesting to you in your field. Most of you are mechanical engineers, but I know there's a few others. So whatever it is in your field, you'll have some exposure to this area to be like, okay, I'm not so intimidated by looking at a schematic that looks like this, that looks like I have no idea what's going on there. So that is what you are going to be doing this semester. By the way, this is a touch sensor circuitry. So where the finger is, that's actually a sensor where on a touch screen it would touch, and this is the electronics behind it interpreting what was touched, where it was touched, and how much it was touched, whether it was a very strong touch or a light touch. So the screens in your phone, in the iPhone, do we now still call it an iPhone? The screen in your iPhone, that kind of screen is what that circuitry does, is it detects when it was touched. All right, so fun. So to begin, we need to learn some very beginning basics. So we need to understand units, we need to understand what is called a current, what is a voltage, and we're going to identify on a circuit now, that scary looking circuit, we're going to identify what's called an ordinary node, an extraordinary node. We're also going to learn the very first techniques called the Kirchhoff's current law and the Kirchhoff's voltage law. And we're going to also being able to identify a branch and a loop of a circuit. So these are the very foundational skills that you need to look at something that looked that scary to be able to analyze that. So that is our learning objectives for today. So before I go into the lecture, I kind of want to just go backwards a little bit to, let's see, I don't have it pulled up. I think it's on my Canvas. So to the Canvas page. So on the Canvas page, let's see. Okay, so on the syllabus on the Canvas page first is some basic information. So free books. So make sure you download the free books and utilize those free books. In the ULB free book, it's weird it's going there. So this ULB Circuit Analysis and Design, they have great companion site. So that companion site will have self-assessments. So that's going to be a great one for you to be able to try problems. Do you understand the problem? Do you know how to actually do the problem? And then when you don't, it will offer you solutions to it too. So then you can learn from that and then continue on and learn and then utilize your knowledge to then retest. So that's going to be a great place to assess yourself. Have you learned this material or not? And so definitely download these books and utilize them. So they are free, which we try to do. As far as the breakdown of evaluations, so 60% is going to be on 4 exams. I do for the final, it's an optional retake of any of the exams in the semester. So if you don't do as well, and then at the very end you do really well, you're like, great, I can have an option to retake a midterm. And then whichever score is higher out of those 2 midterms is the ones that I use for grading. So that's how I work with my lab, or my exams. Labs are required to go to, and the lab will be a separate grade and a separate Canvas course. So do note that you'll have 2 Canvas courses, one for this section of lecture and then one for the lab itself. So on the lab, there'll be a little bit different breakdown of the grading, and then some of that will be attendance and engagement while you're in lab of how you're doing. So if you're not going to be in lab, make sure you're communicating with the TA to say, I'm actually going to go to a different lab section, or I've done the lab on my own, can I just check it off with you? And so you're communicating with the TA so that you get your attendance points. Otherwise, you'll miss out on those. So make sure you're communicating very well with your TA. Let me know if you have any issues with that communication. I'm happy to also assist with the communication, but do make sure you're communicating with the TAs also for the lab work. For the assignments, assessments, and quizzes, typically on Thursdays, you're going to have a homework assignment, and then on Friday, you will have a quiz. So on Thursday, and my homeworks, I've tried to set up where you can reattempt the homeworks until you can get up to 100%. So you can attempt up to 10 times, and each time you take it, you can improve your score. They will be different problems as you take them again, so that's the point of note, that there'll be different problems and you'll need to retake them. So they may not be the same exact problem, but hopefully similar problems, so that you're learning the material and then doing those. So that will be what the homework is for. Fridays then will be an open time period between the morning and evening, so anytime on Fridays, you'll be able to take a quiz that will assess your knowledge, and again, making sure that you understood the homework. Okay, so that will be the structure of those. So the quizzes will be 4%, your homework, practice problems are 4%, and then there's going to be discussion sections each week. The discussion section, there's the discussion assignment is something where you put on there what you may not have been understanding, and then you need to answer from somebody else what they didn't understand and felt like. So people are giving different perspectives on what made sense to them, what didn't make sense, and hopefully you guys are communicating. So you need to post a question on there and then respond to somebody's question on there. Okay, so that's also due on Thursday nights. So Thursday nights will be a homework and a discussion assignment. Fridays will be typically quizzes. The only time when it will not be that will be the exam weeks. You'll have just a exam that week and then a feedback on the exam that will be due. Okay? Any questions about the format of what I expect? Oh, and then there's a final project. So for the final project, at any point in the semester you want to attempt that, you're welcome to start it. And it is basically that you're looking up a application, such as you mentioned here, quantum computers, something else that was interesting to you that we just you guys just mentioned, and then looking at how it works, and then describing it in a presentation format. That is the final project. And so you can do that at any time.
So are we presenting that to you, or is that just being sent like as a presentation to you?
So you can, some students like to present it. So if you like to present it, you can record yourself and submit your recorded video. Or if you are like, I don't like to present at all and I don't want to video myself, you can write it out in just write it out.
Okay.
like you are preparing to present it, and then write what you would say presenting, and then submit that. So you have an option to do it either way. So some people found it easier to like, I just want to prepare and then present it and record that, and then others are like, I don't want to present in front of it, and so just write it out like you would be presenting it. Okay?
We need like visuals or we need like a full presentation.
Yeah, so it needs to be like a PowerPoint type of presentation. So yes, that part is required. And there's rubric on the final project page that gives you some more information about what that needs to contain.
And are those groups or is that just like alone?
Alone.
Okay.
So they are individual.
Okay. Got it.
All right. Any other questions? Yes.
So you said the final is an optional retake of one of the other midterms. Is there also a final you would take if you didn't want to redo midterms, or?
Nope.
Okay.
Nope. It is just the retakes. So there is no comprehensive final. Yes.
Do the retakes take the best score or the most recent?
Best score. So if you do attempt it and you're like, I've totally forgotten that, or I'm way stressed out right now, whichever one is higher. Yes.
So if we're happy with our 4 exam scores, we don't have to take a final at all?
Correct. So if you didn't hear him, if you do well on all of the exams throughout the semester, do you have to take the final? No, you do not have to take the final. So it makes it nice if you've done well throughout, then you have a break for the final period of time. Yes.
So since it's open note with free exam, does that
Yes.
anything?
So the only thing it restricts, so yes, it is open notes and open book. The only thing it will restrict is a circuit simulator. So you cannot use a circuit simulator during the exam, and that is it. So MATLAB's fine if you like to pre-code. I've had some students that pre-code things coming in. Fine to do that and have that ready. Just you include that on your submission work for the exams. And the exams will be taken, I have to make sure we have enough room because I think there was 100 students. So I think they have enough room. So we will hold the exams in one of the CADE labs. And so you will be taking them like, it will be very similar to your quiz attempts. So, except for all together. So we will be all together there.
Are the exams cumulative?
No, so there'll be very specific material on each exam. All right, did that answer your question fully?
Yes.
Okay, any other questions? Okay, you guys are all clear on what's expected for grading? Okay. All right, also on this, I have the schedule. Where did it go? This might not be the right section. Nope, that's the labs. Okay, I swear I put a schedule up here. There it is. Okay. So, this will be the schedule, and so it kind of shows Module 1, Module 2, Module 3, Module 4. And so the first exam will be Modules 1 through 7. Okay, this did not update for the right. Okay, sorry, I did copy this over from the fall. So dates are a little bit off there with not September, it's going to be February 4th, which will be the Tuesday. And then also October 15th, it will not be, it will be February 25th. So just ignore those little typos, but otherwise this will give you an idea of what content will be like on the first exam, what content will be the second exam, third exam, and fourth exam. All right, as far as the learning material then, it's broken up into these modules. So you will need to do this course orientation quiz. Some of that will be what we went through, and some of it means that you have to go look in more detail in the syllabus. So I'm leaving that detail more to you guys. So as part of those quizzes, do look into the details of the syllabus. I didn't feel like I needed to go through all of them. I also have created these practice problems for each unit. So, okay, that one's not published, I guess. Can I not publish it? Okay, I'll have to publish that, I guess, on the other one. But on these practice ones, these will have used databases. So on them, you can start them, and then as you answer them, if you restart it, it will have new problems for you. So you can continuously practice and go through and and these should all have solutions. So let me know if any don't have solutions, because they're all supposed to have solutions. And then I'll just make sure that they get updated. And this will give you, again, another way to self-assess, do you know the material or not, and where you may need to target your learning. So note that those are available. They're actually extra credit, so they're not required. They're very helpful for each exam. So before each exam, I suggest that you also work on those. They're very good practice prep for my exams. All right, and then under the lecture materials, so each has, lecture 1, lecture 2. I haven't updated these, so these are actually videos from last semester, so they'll be updated with current semester's videos. So I will have on there the slides from this lecture, and your slides will say Spring 25 on them, so they're a little bit differentiated. So if you see anything from past semester, it will be very similar, but might be slightly different. So you might want to make sure that you refresh the page to get the right one, or let me know if you see one that I didn't update correctly. And then after the lecture, by the end of the week, I will post the lecture annotated that I go through here in lecture, and then also this video that we do here in class. So if you happen to have to miss a class, then you will have material to work on. Your best way and most efficient way of learning is to be here in class, because we'll do active learning activities in here also. And so this is going to be the most efficient ways to make sure you are here in class. But I do try to provide enough material so if you have missed some, you're still able to go back and watch videos and catch up on the material. And some students, sometimes I go a little fast and they're like, I need it a little slower, so they like to watch the videos again and again to make sure they've gotten the material that they need. So all of that will be available for you guys. And again, if you utilize all of it, all of you can get A's. So please, everybody get A's? Okay. All right, that's what I would hope. Okay, underneath the lecture part, I have these learning material sections. And so underneath the sections, there's some practice links, reading links, video links. And so say you understand scientific notation, circuit elements, terminology, you go to that link, you self-assess, and you're like, great, I got 100% on it. Go to the next subject material. So on this one was current. So again, self-assess, like, great, I know that one just from maybe this lecture experience. You hit voltage and you're like, no sense at all. This makes no sense to me at all. At that point, then you're going to want to read the material very closely, maybe a few times. You're going to want to watch the videos. You're going to want to do practice problems with that type of a problem until you mastered that material. So there is material on each of these sections, so you can delve into it deeper. If you learn differently, knowing your own style, you can figure out what you need to utilize the most. So each one has reading, practice problems, and videos for each of the learning materials themselves. Okay? So hopefully now you understand, like, I do try to provide you with material to learn in what way is most efficient for you, and then it's up to you guys to utilize it. Okay? All right, so that's, again, for each of the lectures, you'll have that. And then typically, because we'll have Monday, Wednesday, or Tuesday and Thursday lectures, and then Thursday will be a posting for the assignment and for the lecture. So here you can see that there's the assignment week 1 discussion, which you can even do after this class if you want. It just is due by Wednesday or by Thursday night. So at any point during the week, you can submit those and then answer somebody's question. And then the lecture 1 and 2 homework will be KCL and KVL. So that will be due Thursday night. It's available now to start. And then your quiz will be on Friday, and I typically try to label it what you'll expect on there. So it will be a KCL problem and a KVL problem that you'll have for the quiz on Friday. Okay, Questions? Do you guys want to learn about KVL and KCL? Okay, so that's what we're going to go back to. Okay, so learning the material. So first off, needed to know units. So units, length, mass, time, temperature, voltage, current, charge, resistance, capacitance, inductance, power, and frequency. So from here, these are the ones that, all the way to frequency, that you're going to see more. So volts for voltage, amps for current, C is your charge for capacitance. Resistance is ohms, or capacitance, C is coulombs, so that's going to be in charge, which is usually Q. So that notation is usually Q for charge, and then C is the unit for coulombs, which is amps times seconds. There we go. Resistance is in ohms, volts over amps. And this is going to be an equation that you're going to have to memorize. This is called Ohm's law. So you're going to memorize this. And it is that I times R, which is current times resistance, is equal to voltage. Or you can rewrite that as resistance is equal to voltage over current. Or your current is equal to voltage over resistance. So memorize one, and then you can manipulate it for any of the other types of equations there. Capacitance is in farads, inductance is in henries, and power is in watts, and frequency typically is in hertz. But we're also going to talk about it as far as being in angular frequency, which is denoted omega, and that unit is in radians per second. So that's going to be the other type of frequency that we talk about. All right, questions about units? All right, common prefixes and scientific notation. So the most common ones are going to be milli, micro, and nano. And then for resistances, typically you'll see killi or kilo, kilo ohms or mega or sometimes giga. So those are going to be the 6 most common ones. But do be aware of the other ones, which you're going to see for different things too. So m, small m, is going to be 10 to the minus 3, micro 10 to the minus 6, nano 10 to the minus 9. All right, 55. Okay, common circuit elements. So you're going to see wires in schematics, and you're going to make some assumptions. So if the two are crossed over, if they do not have if they're fully crossed over and they don't have a dot in the middle, you're going to assume that they are not connected. If they have a dot, then you would assume that they are connected there. If it's a junction where it comes into this, then you would also assume, even without a dot, that those are connected. It's only when they cross over each other, as far as this, that you would assume that they may not be connected. So probably not connected. This is the nicest way to draw that, but a lot of electrical engineers tend to not always do that little zag over it to denote that. And so you'll see it just crossing. And so if it's not a dot with the crossing, then you assume it's not connected there. All right, this element is called a resistor, a fixed value resistance. You have a variable resistor, which has the little arrow through it. This is called a potentiometer, and you're going to use these in the labs. Potentiometer. Okay, and then you have a capacitor, which has the two plates on it. Inductor. So capacitor, inductor, and then you have battery you're going to see in different forms. So a battery could be drawn like this, or a battery could be drawn like this, or a battery could be drawn like that. These are all the same. There are different ways of drawing a battery. And a battery, a DC value battery, is not have the squiggly line that is shown here in the middle. And with the squiggly line, that means it's an AC source, usually a function generator. So in the lab, you get to use a function generator, and you'll use DC sources. Outside of a lab, you can use batteries for your DC supply. So that's why they're just a battery, which you're familiar with. All right, we are not going to address any dependent sources in here. So the schematics with dependent sources, we're only going to look at what's called independent sources. So very fixed values for your DC. So 12 volt, 9 volt, 3 volt, 1.5 volt. You're also going to see current sources, and with a current source, it will have the little arrow in there denoting which way the current is flowing out of this source. So if this is your source and the arrow goes up, that means the current flows in that direction. So it goes out of this source going up, and it comes into the source in the same direction that it is in the source itself. You're also going to see these switches. The switch means that before the time frame of 0, in this case, it would be disconnected first, and then at time equals 0, it becomes connected. So this means there is a full break for time less than 0, and then at time equals 0, it would be a straight wire. Oh, sorry. Okay, so time less than 0, it's open, and then at time equals 0, and greater than that, so greater than or equal to, oh my heavens, there we go, greater than or equal to 0, it's going to be connected as just a connection there. So that's what the switch will look like. So you'll have two different circuits that you'll draw when you see a switch, one before the switch element happens, and then one where it happens after it happens. We'll go over that when we reach the switch itself, but note that that's there. Then we're also going to talk about this later. This is called an operational amplifier. So these are all of the elements that we are going to look at this semester. And then actually, I forgot one. So BJT is our transistor we're going to look at. This is called an NPN transistor. And we're only going to look at the NPN transistors in here. So there's also an NMOS, which is very similar transistor to the BJT, but we're only going to look at the BJT in here. So you'll see that in another schematic. Just note that the different type of transistor basically doing the same thing, whether it's turning on or off and acting as a switch in the circuit. All right, there's going to be a voltmeter and ammeter, which you guys get to use in the lab, so they'll talk more about that in the lab. All right, any questions about the elements that you're going to be seeing this semester? Okay, so we're going to start with current. Okay, so we're not going to get sound with this, so I'm going to describe it as we go, I guess. Okay. Yeah, I don't think it's going through. Let me see if I can put it on this one.
Previously, we talked about how electric charges can build up on surfaces and create something known as static electricity. In this episode, let's talk about what happens when these electric charges continuously move in a process known as current electricity. Most electronics, everything from your refrigerator to your smartphone, requires current electricity to operate. Let's assume that we have a copper wire that's filled with copper atoms. Copper is one of those elements that has only one electron in its outermost shell, which means that with only a little energy, that electron can be easily ejected. If we push a free electron into the copper wire, it will eventually find a new atom to latch onto. The negative charge of that electron will eject another electron from the outer shell, which will then move on to the next atom, and so on and so on. This chain of moving electrons creates a flow known as electric current. Some elements, like copper, aluminum, and gold, can move electrons easily and are known as conductors. We can look at moving charges in another way. Let's say that this tube is a conductive wire and the steel balls are negative electric charges, electrons in this case. We might think that one charged particle needs to move completely through the conductor to create a flow, but that's not actually the case. As we push a ball in one end, the force causes all the balls to move and one pops out the other end. As you can see, one electron, even if it doesn't move very far, can force all the other electrons to move, creating a flow. What we just showed was electric current, which is a flow of electric charge. In most circuits, this is accomplished by moving electrons. The unit for measuring current is the ampere, which is often abbreviated as amps and written with a capital A. 1 ampere is defined as 1 coulomb of charge moving past a point per second. Let's look at a cross-section of wire carrying an electric current. If it takes 3 seconds for 6 coulombs of charge to move through that cross-section, then we say that 2 amps are moving through that wire. Unfortunately, electric current doesn't just magically flow through wires. It needs a little help. If left alone, the electrons in a wire won't move. We need to give them a little push. To do that, we'll use a voltage source like a battery. In a battery, there is a buildup of negative charge on one side in the form of excess electrons. The other side has a buildup of positive charge, an absence of electrons in this case. The charges want to balance out, but the only way to do that is for the excess electrons to flow around the battery through a conductor that we provide. If we connect a piece of wire to the negative terminal, the electrons will push against the electrons in the wire. However, air is an insulator as its molecules do not have very mobile electrons, and it won't readily accept the free electrons. To show this, we'll put a piece of tape at the end of the tube.
So, to make a side comment, this is just like a dangling wire. So if you do not connect it to anything at the end, this would be the same thing that happens if you create a circuit and then you put a wire and it doesn't connect to anything else. So we're going to see that in schematics where it will just be, oh, it's this dangling wire sitting out there, and it's going to have the same effect that you're going to see here.
Now, the electrons at the end of the wire have nowhere to go. Even if we push against the electrons in the wire, they still won't budge. To fix this, we need to connect the other end of the wire to a place where the electrons want to go, and the positive end of the battery will happily accept the electrons. In fact, don't try this with a real battery. There is nothing slowing down or restricting the flow of electrons, which results in tremendous amounts of energy being transformed into heat in the wire, and this could easily melt the wire insulation or start a fire. This is known as a closed circuit, as it creates a loop from one side of the energy source to the other. If we break the wire or remove it from one of the terminals, then the electrons will stop flowing. This is known as an open circuit. We've been talking about electron flow in a circuit and showing how electrons move from the negative terminal to the positive terminal. However, in electronics, we usually assign current as flowing from positive to negative, or from higher potential to lower potential. This is known as conventional current. In the mid-1700s, Benjamin Franklin theorized that positively charged objects had an excess of what he called electric fluid, and that negatively charged objects had a deficit of this fluid. Franklin noted that this fluid had a tendency to flow from positive to negative to distribute itself more evenly. It wasn't until the end of the 19th century that English physicist J.J. Thomson discovered the existence of the electron. Even though we now know that it is electrons that move inside of most circuits from low to high potential, the convention of current moving from high to low potential stuck. As a result, most current measurements are given as conventional current, which is the movement of positive charge in a circuit, and is represented by the capital letter I. Don't worry, the math still works out as long as we stick with either electron flow or conventional current. And since most electronics textbooks use conventional current, we'll go with that. We talked about making electricity do work for us, and the circuit forms the basis for all modern electronics, everything from the simple flashlight to massive supercomputers. If we made a circuit out of just a battery and a piece of wire, there's a chance we might melt that wire as the electrons move through that wire at an alarming rate and generate massive amounts of heat. In the next episode, we'll talk about the relationship between voltage and current and introduce the resistor.
So this is, a nice explanation. So if you want to also go here, it has other explanations like from the Ohm's law that I gave, also for voltage and so on. So I encourage you to go to this link also if you have liked this one and like to have that explanation also for other topics that we're going to discuss. Okay, so they were saying don't hook up directly your wire to the battery because it will melt. This was thanks to one of our U of U students in EE. They did this experiment where they actually were showing physically this will start to bubble up on the potato. And so it's kind of a fun little thing. So putting that in there to provide your resistance, you can actually see the bubbles on the side of the potato, leaving it overnight. On the other side, you'll start to see that green spot and then it will migrate. So it's kind of a cool little experiment if you guys have any interest in that. It will also show you a little bit more in a demonstrative way the flow of the electrons as you see it actually moving through the potato. All right, so we're gonna go now into a schematic. So thinking about just a battery with a lamp on it. This is going to be what we call an LED, a light emitting diode, is also a way to define a lamp. And the schematic for that is this right here. So you're going to have this little triangle with a line on it, and then the two arrows out means that it's giving off light. So that's another symbol that wasn't on the previous one. So looking at just having a switch between a battery and a light itself, you can redraw that as this circuit. This would be your switch portion. And then if you're only looking at it in one time with it closed, you would just have it be a closed wire there. So from that video, it talked about this I current going from positive to negative. So what we remember is that the negative side is always on the arrow side. So when you draw the current flow from the plus to the minus, usually it comes out of the plus side of the battery, and then you would have plus to minus labeled polarity as that. So note that that is the same as if I drew this kind of funny looking schematic where there is a wiggly line in between the battery and that lamp. These are the same exact circuits. So even though I've drawn it very nicely connected with a square wire there, it can be a meandering wire to get to the other thing. So a wire is not a physical location. It can be long, it can be short. It's just a representation that it's connected between this point and that point. So when you guys go to lab, you're gonna see on a breadboard is what they're called. There'll be a little wire, or there'll be a line, And within that line, there'll be connections in between them. That will be the same as having the wires here. And then externally, you can have a short wire between elements, a long wire between elements. It doesn't matter. It's just the matter of the connections between them. Okay, so that's one thing I know that students have a harder time with first visually, is understanding that that is not a representation of a physical distance when you see the wires there. Yes?
If we wanted to have a representation of physical distance, if we're worried about like inductance or something, is there a convention for that, or?
So that would be more on like a mechanical drawing where you would have a physical length, and then that length would have like some type of resistance or inductance or capacitance to it depending on what it's made out of. And so that would be the mechanical drawing side, which you guys all now probably know. And so that would be different information that you're looking for on such a drawing. So yes, there are some, but they're not giving you electrical information. They're going to give you the mechanical information from it. And yes, well, I guess I should say that back. So yes, the length will determine like some capacitance or resistance or inductance. What we call that is a parasitic effect. And so when we design or we're analyzing, we usually ignore those parasitic effects and let a simulator usually tell us more information about that. So on a hand-drawn schematic, we would ignore those issues. All right, any other questions so far? Okay. All right. So again, memorize that on the conventional current drawing, the arrow is going to be your negative side. So this is what we're going to use when we move to the next techniques of that KVL and KCL. Okay. Okay, I can't remember. Okay, so this is just going back into the course pages. I couldn't remember what that one was. Okay, so KVL and KCL. KVL is Kirchhoff's voltage law. KCL is Kirchhoff's current law. And so what the voltage law, or I'll start with the current law, I guess. So what the current law says, sorry. Okay, so what the current law says is that whatever it's the summation of currents that are entering or exiting a node. You get to pick which way you like to define it. So in this case, if you are saying, as my current enters, that's going to be the positive, and anything exiting is going to be my negative, you would sum all of those currents and they equal 0. So basically, if you guys are more familiar with probably flow through pipes, like water flowing through pipes. So as they come into a junction, they combine and create the summation of both of those into one junction. And that's the same thing for current. Whatever comes in basically goes out, and the net summation of those is going to equal 0. So if you like that analogy of the water, it's the same idea as far as what comes in has to go out, and that summation is going to equal 0. So for the first one, if I1 coming in is positive, I4 coming in would be positive. You see those positives here, and then I2 and I3 are going out, so they would be negative. So if you like that, then you could use those conventions, or you could leave those leaving a node are positive, then you would have the opposite of the first equation. So whichever way you like to write it, you just stick with that convention and then don't change. So pick a convention you like and then always do the same thing. So do it different ways for different circuits, and then whatever one you like, be like, I like this way. I find mechanical engineering students for some reason like the last one the most. So it's setting them equal to each other. So whatever comes in equals that going out. And I've also found that as mechanical engineers, you guys typically like to do that with voltage too. Like you like to sum it up to some point and then say it equals that value. So if you like that, great. If you don't, that's fine. just pick whichever one you like. So the last one is just setting it equal to each other. So whatever comes in is equal to whatever is going out. So this is the Kirchhoff's current law. Okay, this did not. Okay. 18. All right, so, well, let's do some practice problems first with this one. Okay. Nope, it's not letting me. Okay. Okay. That did not get erased previously, sorry. Okay, so I like to highlight every wire that's in the circuit. So I suggest coming with pens, markers, pencils that are colored, crayons, whatever you kind of like. If you have a tablet, it's nice because you usually have options for different colors with it. But if you like to write still on paper, I suggest printing out the circuits that we're going to work on in class, and then coming with markers or pens or coloring. So, didn't know you guys were going to color in this class, but you will. So a node is just a wire that's all connected between elements. So that is the definition of a node. So, node. It's a connection between elements. So I first have to identify my elements. So here's one element, the resistor. Here's another element, resistor. Here's another element. What's that one? Battery. Here's another one. Resistance. Another one. Resistor. And okay. So identify the elements first. And then as you get more comfortable with it, you won't have to like highlight them like this. But I do suggest in the beginning, highlight them first. So draw a circle, box around them. And then you're going to draw the coloring in between each of those elements. So this one's already labeled, but you're going to highlight, that would be, you would highlight all the wires until you hit the other side of another element. So that's why all of the blue is highlighted there. And then the pink, I would be highlighting all this. And you highlight until you hit an element. So all of those are now going to be considered the same node. So doing that with each. And then you can label the nodes. So I labeled the blue one node 1, the red one node 2. I erased the node 3. Green is node 3. And the bottom pink would be node 4. So this one has 4 nodes. So with that, then you look at the currents that are going in and out of the nodes to be able to do the current summation. So every element is where you're going to draw the current. So if it is not labeled, you're going to make an assumption of the direction. And there's no right or wrong assumption of the direction. So I can already see that there's some labels already in here. So I'm going to stick with kind of the option of whatever direction. And since they're both basically flowing in this direction, another visual thing that you'll have to get used to is the bend in wires. So I know it looks weird, but that just means that the flow continues in the same direction it was labeled. So if I label on this wire in this direction, it means it's going to continue around that corner in the same direction. So that takes a minute usually for students to understand that concept. Everything in a branch, so a branch, okay, actually let me back up. So two types of nodes. First, one's called an ordinary node. And an ordinary node just has, it's the wire or connection between two elements. You then have extraordinary. And it has more than two connections. So connection between, connection with more than two elements. So the pink one, how many elements are connected to it? 3. So is it an ordinary or extraordinary node? Extraordinary, correct. So I'm going to call this E and this one O. So this is an E. What about node 1? Extraordinary or ordinary? Okay, so I have 1, 2, 3 elements off of it. So this would be also extraordinary. Node 2? Correct, extraordinary. Node 3? Okay, so in this example, all of these were extraordinary. But there is situations where you're going to see some ordinary ones. Okay. Between two extraordinary, so I think how to say this right. So now we have the terminology of branch and loop. So a loop is going to be continuous pathway from start to finish, from same point. I'll just put same points. Okay, so a loop would be a pathway, okay, purple. So say I start here at the N4, I go up through this element, and I go through I5, and down here, and then I go back to the same point that I started. That would be considered a loop. A branch is going to be, if you have ordinary nodes, they're going to be in the same branch, and a branch is a connection between two extraordinary nodes. So for this example, you have N3 and N4. So N3 to N4 is a branch. There's only one element in it, which is this element here. That would be considered a branch. You also have between N2 and N4, which are both extraordinary nodes, this element here. And again, that would be the only element in that branch. Same thing for the battery. It's a connection between N1 and N4, which are both extraordinary nodes, and it would just be one element in that branch. The reason I'm defining these terms is that in a branch, so this is the most important part, in a branch, you can only have one current. So that's the takeaway from these terms, is that in a branch, you can only have one current that flows between them. So, because you can only have one current in a branch, and I'll keep going back to that, we said that the battery here was the only element in that branch. So because we can only have one, that means that I1 and I7 have to be the same current. Does that make sense? Okay. So because of that, I1 has to equal I7. All right, now we can set up the equations so that we can do the Kirchhoff's laws, current law, and actually get values. So if we're given I4 is 20 milli, I5 is 10 milli, and I6 is 22 milli, can we solve for I1, I3, I2, and I7? Okay. Go ahead and try this on your own for a minute. Try to write the current summations for node 1, node 2, node 3, and node 4. And just go ahead and do these individually, or if you want to work in very small groups. Introduce yourself to your neighbor. If you have not met your neighbor yet, go ahead and introduce yourselves to your neighbors and take a couple minutes to write these equations. You'll just All right, hopefully you guys have met a new friend today. If not, hopefully you guys found these. So the summation of the current, so for the node 1, hopefully you were able to find, and I'll try to write, because as I said, I found that last semester mechanical engineers like to write this way better. So I1 going in equals I2 plus I3. So I2 and I3 go out, I1 comes in. So hopefully, also visually you can kind of see that. Node 2, I3 comes in, and then I4 and I5 go out. So I3 equals I4 plus I5. For node 3, I2 plus I5 come in, and then I6 equals I6. So again, you have to note on that top one that with the element here, that's where the branch is. So whatever comes in goes out. So all of the current in this branch is going to be the same, and that will be I2. So with that being the branch, all of that current is I2 that goes through it. All right, node 4, you have I4 plus I6 equals I7. And then I1 equals I7. Any questions on getting these sets of equations? Anybody have any difficulty? Okay, so then solving that should end up being with I7 was equal to I1, so 42 milliamps. And then just manipulation, like I2 will be a minus 10 plus 22 milli. So in my current summations from last semester, you can see that I actually did write these a little different, but I will try to write them consistently going forward. And then I2 would be 12 milliamps, I3 30 milliamps, and I7 42 milliamps. So as an exercise, go back and make sure you can solve those to get those same values. Okay, any questions on this problem? Okay. I don't think I want to talk about that one. Okay, so the voltage law. So a voltage law is going to be around a closed loop. So that is the key for this one, is you need a closed loop. Or defined voltage or defined voltage. So in this, you can see hopefully that this is a pathway from start to finish. In this case, it has elements across for each voltage that's labeled there. So the voltage is a plus minus description, and you're going to see it next to an element. What that means is that even though it's not written, that means that the locations on each side are actually going to be the plus right next to it there and the minus right next to it there. So you will see that very commonly, though, just written next to the element. But that means on the wire itself is that voltage. In lab, you're going to use what's called a voltmeter, where you're actually going to put a wire on that physical location and on the other side and measure it. So you'll get that idea of what that means to have the voltage plus and minus just next to an element. But visually, for a little bit, you'll have to kind of remember that it is, even though it's next to it, it means it's on the wire itself and that location. So here that plus is right here physically on the element, and the negative is right here on the element. And again, right here and right here. So what I meant by it needs a closed loop or defined voltage is you can still take a loop if you define a voltage difference between two locations that are floating in air. So in that video, remember with the current, if it was open, there was no current flow. So the current flow will be 0 in an open connection, but there can be voltage difference between those two locations. So you can still do a voltage loop when you have a defined voltage between one location and the next, as long as it's giving you the pathway back to the start. So in this case, you're going to do a summation of voltage will equal 0, and that's the law in this case. So I physically ask you to physically put down your pen or pencil at the start of the pathway. So here, so if I start here, I'm going to physically move my pen or pencil, and in my case, the Apple Pencil, around in this loop, whichever direction I call it. So I kind of went around in this direction. I'm then going to circle the polarity as I go through it. So as I go through it, I'm going to circle the polarity. So that would be plus here, and minus here. And that would be my summation. So this would be a plus VDC, a minus V1, and a minus V2 equals 0. And that would be how I would write that voltage loop. So again, the steps were to pick your starting point. Well, first off, I guess you need to make sure that you have labeled so you label the polarity on every element. So this is the first step, is to make sure you've labeled the polarity on every element. You pick a starting point, and then you physically move your marker pencil, Apple Pencil, whatever it is, around the loop. And as you go through an element, you circle the polarity of the second one always. Okay? Then you write down that as your polarity. So this would be plus VDC, minus V1, and then a minus V2. Okay, questions on that? You guys ready to tackle one? Okay. So you're going to pick your voltage loops, and then you're going to solve for VS, V4, and V2. Again, highlight the nodes. So I'll highlight them again for you. And then pick your pathways. So there's going to be several different pathways. Again, it's start, back to start. I'll do the first one with you. So here, I could say, like, let me take the pathway through here, and I'd be going in that direction. This would be plus, minus, minus. So plus VS, minus V3, minus V4 equals 0. Okay, probably 2 minutes. Again, you can work with your neighbor or your new friend that you've met and be able to do, let's see, 2, 3, maybe try and do 4 loops. So write equations for 4 loops. Oh, and I forgot to introduce, so Zara is your TA for this course, so she's going to be attending in here. You can ask her questions throughout class since we have a large group of students. Figuring having 2 people you can ask questions to. You can also set up time to meet with her outside of class, and she'll have office hours also. Nice to meet you. All right, so here are the equations that you could come up with. There's going to be two more that you could actually do to create loops. I think there's one more. There's three. There's three other ones that you could actually. Yep. So you could go around. So that was my VS. That was around the whole outside. So there's two other equations that you could come that would be unique to this. Exercise is to solve those to get 6 volts, 3.7 volts, and 2.8 volts. So this is your homework, similar to your homework that will be due this Thursday. So you guys have enough knowledge you can actually attempt it. And then the quiz will be circuits like this that you'll need to do KVL, KCL for. Yeah. Oh yeah, no lab this week. No lab this week, and labs will start next week.
It says like online assignment. Like on campus, didn't find it.
Oh. Okay, I'll send an announcement if there is. Thank you.
I sent you an email.
Uh-huh.
It said you're getting a lot of emails, so I figured I'd try to help you.
Yes.
I am in one of the later labs on Tuesday.